Welcome back, everybody. This is going to be a really important tutorial on not only how to complete the practice questions from our learning of electric fields, but also on how to really appreciate this idea of voltage versus charge. So please ensure that you have page 2 of your period or your data booklet ready to go, and your scientific calculator. I'm going to go through each of these questions separately, and if you need to, just please ensure that you are pausing this video and then recording your steps as we go. So in the first question, we need to find the electric field strength. So right away, I can say that I know I need to find big E. That's what it's telling me. We're 20 meters from the source, so I know that that is my radius. And it looks like I have a positively charged sphere, and that has a charge of 0.03. Now, this positive value here simply tells you that it has lost electrons. Okay, so don't worry too much about that until we get to the end. So what I'd suggest you do is you list what you need to know. So I know that the question is my electric field. I know that my charge, my Q, is 0.03 coulombs. I know my my electrical constant, because it's always here on page 2 in my data booklet. And please make sure, again, you know how to type in that exponent. And then I know my radius, which is 20 meters. Now this question, we're good to go. That is in meters, so that we should then not have to worry about converting that. So if you type everything in, and I am just going to leave out the units for now, just for simplicity. Hopefully you are able to follow. Okay, now again, just make sure that when you have it on the bottom, you are going to square this value. So if all is said and done, you're going to get a fairly large number of just over 600,000. Okay, so 4,250, and I'm going to get newtons per coulomb. Now this is okay to leave this answer as it is, but as always, we're going to try and tidy it up and put it into scientific notation. So if I take a look, the value of 20.0 has 3 sig digs, and 0.0300 has 3 sig digs. So ideally, we're going to put this into a nice scientific notation of 6.74 times 10 to the 5th, because I would have to move that decimal 5 times to the left. And again, this is newtons per coulomb. And if I really wanted to make sure I understood the way of the direction of this field, because it's a positive field, it would be pulling away. Okay, because I have a positive source and a positive test body. Okay, so again, this would be an added bonus. So if you need to pause this video to make sure that you can follow along and that you are able to track that. For number 2, please list what you need to find out. So again, what is the electric field strength? So it's asking me for big E, and I've been given a distance here of 7.5 to the negative 1. So essentially, this is the value, if I were to draw it out in expanded form. And it says from an 8, weird value here, coulomb. So the reason why I've put this value here is this is a micro coulomb. It's very, very small. So this is going to be a really important trick with you look at conversions. So this is a charge. This is my Q, but you always need to make sure you always give this value in coulombs or Cs. But right now I have a micro coulomb. So this is no different when we had to go from centimeters to meters. And I'm going to show you probably the most important trick that you're going to pick up in Science 30. So let's list everything first, and then I'm going to show you that trick. I don't know the electric field strength. That's what I'm trying to figure out. I know that Q, it says right here, was 8.00 microcoulombs. Here's how you're going to convert this. Write down the original value, which was 8.00. Now go to your data booklet and pick up the conversion factor. So right now this says times 10 to the negative 6. So if I were to convert this, I'm literally going to take 8.00 and I'm going to divide it by basically 100,000. That's essentially what this is, okay? Or 0.000001. So it's easier just to write it like this, and now this is a coulomb. By me writing in this notation, I have just converted it, and it's the easiest way to use this conversion factor, and this is on page 1 in your data booklet, okay? So it's super important I get my coulombs or my charge in coulombs. My K, we always know this now, at 8.99 times 10 to my 9th. Again, I'm going to leave out the units just so that we don't confuse you, and then I know that my distance or my radius here, it's already in my meters, so I don't have to worry about that. So now all I need to do is fill in my equation. Okay, So again, I'd always recommend you write in your equation first, okay, so that you don't lose track of where things are. And now you just need to plug and chug. Okay, so this is going to be 8.99 to the 9th. Please again ensure that you're using your exponent button and not multiply 10. I've just done a really important step here by converting this. Okay, so make sure again it's to that -6th, and that's now a coulomb, and my distance is already set and ready to go. And again, ensure that you are squaring this value. So if you do everything correctly, you again are going to get a fairly large number. These electric fields are quite powerful. So if the calculator and I are working properly, you should just get over 127,000. Okay, and if you just write out the rest, again, this is going to be in newtons per coulomb. Again, we're going to tidy this up if at all possible. And if I look, I've got 3 sig digs and 3 sig digs. So that means I'm going to change this to 1.28, and I need the rest of those values to the 5th newtons per coulomb. Okay, and again, you could even try and figure out the direction. Unfortunately, we don't know the positive or negative charge of that 8 microcoulomb, so we're just going to leave that. So again, pause this, go back if you need to, and ensure that you are comfortable with this step of converting those microcoulombs to coulombs. This is probably the easiest way of doing it. When you look at question 3, again, you have to figure out the electric field strength. So some of these are going to be repetitive in nature. So again, this is the question. I can just write that. Now, this is a slight typo. This should be 10 meters on the left. Sorry, it just kind of got put together. To the left side of an electron. Now, you know that electrons are negative. That's going to be important in a little bit. I've just told you that the charge of an electron is negative 1.6 to the 19th. I have just told you your Q. That's your charge. So if I list out what I need to know, I want to find out my electric field strength. I know my constant. I always know that. I've just been told that this is apparently is the charge of an electron. Now I'm going to write in that negative, but that negative is simply telling me the charge of it, okay, because electrons are obviously negative, and the radius or the distance, this is 10 meters. So sometimes it is important to draw this out. So if I'm going to draw this out, here's my electron, that's my source, and this test body that we're being asked about is going to be right here. This is 10 meters to the left of it. So now we just have to calculate what is the electric field strength out here. So now that I have everything and I'm good to go, I just need to now put in my values. So again, I have 8.99 times 10 to the 9th. That is my constant. My charge, I'm not going to worry about my negative value. That's simply telling me that the fact that that is a negative source. I'm going to leave that out of my math. I don't need it. If you put it in, that's okay too, but you don't need to. And then I'm going to make sure I put in my value on the bottom of my 10 meters. Now, if I again do everything correctly, what you should be getting is a pretty small value. I should be getting 1.4384 times 10 to the -8, again, newtons per coulomb. If I wanted to clean this up, I only need 2 significant digits, so this would be basically 1.5 times 10 to the -8. And then I can even tell you which direction I'm going to feel this. Because this is an electron and I am always going to be a positive test body, I am going to feel this force being pulled towards me. So I am now going to have to write in my brackets that I am going to be attracted or towards this source. Okay, so again, there's a few extra steps there. Please ensure that you can follow along. Now, when we get to this final question, or when we get to question number 4, again, please make sure you can sort of understand what it is we're trying to ask you. So it's now asking what is the charge. So this is now very, very different because we've been calculating electric field strength. So we're now going to be charged in a way with calculating the charge. So Q is my unknown. So we're going to have to redo this formula. I know that my electric field strength is just giving me this as 15 newtons per coulomb. And again, I can just use my data booklet on page 2 if I can't remember that that is my electric field strength unit, okay? And I have my distance of 1.2 millimeters away, and I'm always going to know my constant, okay, of 8.99 times 10 to the 9th. Now, there's a few tricks here. Number 1, we're going to have to deal with getting the equation in the right way, but this radius also needs to be dealt with. So again, I can use page 1 of my data booklet, and if I find a millimeter, and if I look across and I kind of look at its equivalent, it is to the negative third, which again, there's 1,000 millimeters into a meter. So I am going to convert this by simply writing down the original number of 1.2 times 10 to that conversion factor of -3, and that's now in meters. Okay, so this is a super important section. So the next thing I need to make sure I can do is I need to be able to rework my formula, and I need to put charge in the driver's seat. If you need to, pause the video and work out how I can take my original formula and then get my algebra to cooperate and get Q. So once you've hopefully been able to do that, and I now write in my values, again, this is the first time we're going to have the radius on the top, so please make sure, again, when you do this, I have to square that value, super important, and then I'm going to have my constant now on the bottom. So that's the first time we've seen that. Again, when everything is said and done, and you should be able to rewrite your formula, and if your math is correct, hopefully the charge value that you are going to see is 2.4 times 10 to the -15th. Okay, so that charge is really, really small. And again, because this is going to be negative, okay, so this is the important part, it's going to be a negative charge, it's going to now be towards. So I'm going to put in brackets towards, and that's going to be a great way of finishing. So if you have any questions, again, pause this video, go back and make sure you can understand it. So question 5, again, we're now just continuing to sort of add on what we've done before. So I now have, again, 2 balloons. I've drawn them down on the bottom for you, and it's a dry room, and they're suspended by a string. So what we need to be able to do is we need to take a look, and we want to figure out the electric field strength that's between them, okay? So if you were going to draw this, that's one of the first things we asked you to do. Could you actually draw what's going to happen? So if I have a negative balloon here and a negative balloon here, could you actually draw in your field line? So remember, these two are going to push away from each other. Okay, so I can draw those in the middle. I'm going to have that repulsion in the middle. But again, everything else, every other field line that's around this balloon is going to be attracted to it. Why? Because remember, every test body we put in the middle is positive, and it always goes from positive to negative. So this is job number 1, is can you actually draw that in? Now if I wanted to calculate my electric field strength, again, we need to make sure we can actually calculate and we can round up all of the values that I need to have. So if I wanted to figure out my electric field strength, that's the question, go through and list what you know. I know that the charge is -0.5. Now this is an NC. This is a nanocoulomb. This again is an exceedingly small number. So go to page 1 in your data booklet, find the N, read across, and you're going to see that its equivalent is times 10 to the -9th. And that's again to the base unit, which we always understand would be in meters, but because this is a charge, its base unit is a coulomb, and that's what we want. So this is going to be a really quick and important conversion, is that this is now going to be 0.5 times 10 to the -9th coulomb. I need to have this conversion in order for the math to work out. So if we keep making sure we have everything we need, that was my charge. And then if I round up anything else, I think I was given my distance at 22 centimeters. So again, another little trick, I need to convert this to meters. So I can do one of 2 things. I can do the same conversion above, or I can now just divide this by 100, because there's 100 centimeters in a meter, or I can write that this is 22 times 10 to the -2 meters. Either of these will work. Most of you, I think, will be okay with that conversion that I did. And then, of course, I always have my constant. Okay, so now when everything is said and done, can you actually finish B? Can you actually calculate this? So hopefully when you put everything in, the field strength that you should be getting is 92.8719 newtons per coulomb. If I again round this and I make this nice and pretty, and again look at my sig digs, I only need 2, it's 93 newtons per coulomb. And if again you take a look at which direction, this is going to be towards, because I am in the middle of this. I'm going to feel this pull inwards. Okay. Now the last question, what it asks for C, is it asks for the electric field strength at the midpoint. So the midpoint is the one right in the middle. So this hopefully is if you can kind of understand this. If I understand this correctly, because they're being repelled, this direction on this balloon is going away at 93 newtons per coulomb. But again, remember, the one on the right is doing the exact same thing. It's being pushed away at, again, 93 coulombs, newtons per coulomb to the right. So if I take a look right down the middle at the exact midpoint, the overall field that I'm going to feel is going to be 0 newtons per coulomb. Because think of it this way, to the left I have sort of a negative direction, and to the right I have a positive, and they're of equal value, so that means I am going to feel, again, it's like I'm suspended in mid-air. So that's kind of a neat way of looking at those balloon questions. So again, pause this video if you need, and make sure you're ready to move on to charge versus separation of charges, where we're going to look at the concept of voltage versus current.